Chemical Kinetics, Part 3. Method of initial rates to determine differential rate law for reactions with multiple reactants, like this one, where we have chemical A reacting with chemical B to form products. When there's a reaction with multiple reactants, the differential rate law looks like this. The rate of reaction is equal to the rate constant K times the concentration of chemical A raised to the m power times the concentration of chemical B raised to the n power, where the reaction is m order with respect to A, or we could say it's m order in A, and n order with respect to B. The sum of the orders of the individual reactants give us the overall reaction order. Here's an example. Let's say we have a reaction with this rate law, where the rate of reaction is equal to K times the concentration of A to the first power times the concentration of B to the second power. We would say that this reaction is first order in A, second order in B, and 1 plus 2 is 3. It's third order overall. So when you have a reaction with multiple reactants, determine the order of each reactant separately by ignoring the reactants that have constant concentration from one experiment to another. Here's an example. We have A plus B forming products, and we have two experiments set up. Notice that in both experiments 1 and 2, the initial concentration of chemical A is kept constant. And that from experiment 2 to experiment 1, we see a factor of 2 difference in the concentration of chemical B. We run the reaction in both experiments and measure these initial rates. So we can use this data to determine what's the order of reaction with respect to chemical B. What's the order of reaction in B? Now remember that the rate law has this general expression, and what we're going to do is plug in the values from experiment 1 into this expression, and then plug in the values again for experiment 2 in this expression, and then divide this equation out for experiment 1 divided by experiment 2. So here's experiment 1 on top and experiment 2 on the bottom. And typically when you do this dividing technique, you want to take the big numbers divided by the small numbers. So I'll put experiment 1 on the top. The rate for experiment 1 is 4.3 times 10 to the third molarity per second. And then the right-hand side of the equation for experiment 1 is 0.5 molarity, well, K, I guess we start with that, and then 0.5 molarity for the initial concentration of A raised to the m power, and then 1.5 molarity for the initial concentration of B raised to the n power. Now for experiment 2, we have 2 times 10 to the third molar per second. And then we also have K in that expression. The concentration of A is again 0.5 molar raised to the m power. And the concentration of B in experiment 2 is 0.75 molar raised to the n power. So again, these are all data points from experiment 1 and here from experiment 2. And we divide out this equation for experiment 1 divided by experiment 2. And what we notice then is, first of all the units are going to cancel out. Molar per second divided by molar per seconds cancel, molar divided by molar cancels. Second of all, anything that's common to the top and bottom will cancel. So K divided by K cancels. 0.5 molar to the m power divided by 0.5 molar to the m power cancels. So we end up with 4 times 10 to the third divided by 2 times 10 to the third, or 2 on the left-hand side of the equality. And on the right-hand side of the equality, 1.5 to the n power divided by 0.75 to the n power. Now it's a property of math that we can rearrange this and say that it's equal to 1.5 divided by 0.75, all raised to the n power. 1.5 divided by 0.75 is 2. So on the left-hand side we have 2, and on the right-hand side we have 2 to the n power. If we solve for n, we get that n is equal to 1. And you could really just guess and check that, right? So the reaction is first order with respect to chemical B. Now, you don't really have to do this dividing technique. If you're solving for a negative reaction order or a fraction reaction order, then this is probably the technique you might want to consider. But there's an easier way to do it without doing all that math. This is the same experimental data that we just looked at. What you can remember is this trick that reactants with constant concentration should be ignored, as they will have no effect on the change in rate from one experiment to another. So, seeing that the concentration of chemical A is constant there, we can just ignore that. Now we can notice that from experiment 1 to experiment 2, there's a factor of 2 increase in the initial concentration of chemical B. And as a result of that, from experiment 1 to experiment 2, there's a factor of 2 increase in the rate. So we increase the concentration by a factor of 2, and the rate increases by a factor of 2. That shows a direct proportion between the change in the concentration and the rate, and that would indicate a first-order reaction. Let's take a look at an example where we can determine the reaction order of every reactant. Here we have, again, chemical A plus B forming products. Here's our general rate, differential rate law expression, and we're going to find M, the reaction order with respect to chemical A, and N, the reaction order with respect to chemical B, and we're going to do so by determining the order of each reactant separately. So let's see if we can determine the order of reaction with respect to chemical A by finding some experiments where the concentration of chemical B is kept constant. We see that's happening right here between experiments 2 and 3. So let's ignore, in experiments 2 and 3, let's ignore chemical B, and let's look at what's happening with the concentration of chemical A and the initial rate of reaction. So from experiment 2 to experiment 3, we increase by a factor of 2 between experiments 2 and 3. And from experiments 2 to 3, we see that the initial rate of the reaction is constant. So what does that mean when, if you change the concentration, you get no change in the rate? Well, that means that the order with the reaction with respect to that chemical that's changing, in this case chemical A, is 0. And again, we did this by comparing experiments 2 and 3, where we had constant concentration for chemical B. Now let's find the order of reaction with respect to chemical B. What we're going to do is find some experiments where the concentration of chemical A is constant, and that happens in experiment 1 and experiment 2. So let's compare experiments 1 and 2, ignoring chemical A, because with constant concentration, A will not affect the rate. All right, so then what we do from experiment 1 to experiment 2 is we see a doubling of the concentration of chemical B. And when we look at what happens with the rate, we see a doubling of the rate. Now, sometimes you'll see decimal numbers here that are not as easy to calculate in your head. That's fine. Just take the big number, punch it in your calculator, and divide by the small number, and that'll give you what that factor is. And if you don't see a one-to-one relationship like that, look for squared relationships. Remember that reaction orders can be 0 or 1 or 2. If there's 0 order, a change in the rate will have no, or rather a change in the concentration will have no change in the rate. It'll stay constant. If it's a first order like this one, changing the concentration changes the rate directly proportional. So we double the concentration here, we double the rate. And if it's not constant and it's not a one-to-one relationship, then it's likely going to be a second order reaction where if you change the concentration, the rate of the reaction changes by that same multiplier squared. All right, so we can see that one-to-one relationship means that for chemical B, the order of reaction is 1, so the N value is 1. And again, we did this by comparing experiments 1 and 2 where we had a constant concentration of chemical A. So we can be a little bit more specific about what our rate law looks like. Now the rate is equal to the rate constant K times the concentration of A to the 0 power times the concentration of B to the first power. And A to the 0 is equal to 1. We can omit that. and b to the first power is just equal to b, so we can get rid of that 1 there for a coefficient or for an exponent, and we can just say that the rate is equal to k times the concentration of chemical B.